So I'm still yet to receive all the tests. I'm missing one. I'm, let's say, very unhappy. We'll see if the person drops or something or has an answer for. But no matter what, we're going to be moving on. If the person eventually hands in the test, I mean, I might make a special video just to go over the crib and post that for when I get all the tests, and that way not spend a class period on that. We are ready for test 2. I will maybe send that out later today, send instructions with that. It's very similar to the test we just went over on Monday. Very, very similar. If you can do most of the stuff we went over on Monday, you should be able to do 2/3, 3/4, something like that of the test. So look for that in your email box shortly. I'll send it through there, and I'll also send it set a reminder on Google Classroom. I also sent an email recently about turning in lab reports. I know we didn't have lab, but the 6-week grading period ends this Friday, so I'd like to update people's grades as much as possible. So for that, I need at least one lab report from everyone, and I think most people have done at least lab 2. So finish that up, send me a picture of the results of that. I'd like to update that, grade those, and get those in the grade book, and that way I can give you all like, oh, they're doing just fine and dandy. Because I think as long as you've come to at least one lab, you should be doing just fine and dandy. But if you have no real lab scores, it's like, ugh. So get that to me. Technically, yes, you should be doing online labs, but we'll get there when, I mean, those are more of can be done anytime. And right now, if you don't have the stuff, the material you need for it, obviously the snow day is making it a little hard to say do that. But okay, I am going to go ahead and start the new material, which is covalent bonding. This will be test 3 material here. Now let's just take a look at this. So previously, last chapter, we were looking at ionic bonding, which was the attraction, repulsion between two opposite charges. So with the formation of a covalent bond, it's kind of opposite from this. Instead of transferring electrons so that a cation can be attracted to the anion, the valence electrons will share electrons in what's called a covalent bond. Now, they're going to share electrons until they get the noble gas electron configuration. This Lewis theory teaches us that we're going to try to get that noble gas electron configuration of 2 in the S, 6 in the P, or 8 electrons total. Atoms will gain, lose, or share electrons until they get that noble gas electron configuration. Now, why this is so stable is because there is such a high energy barrier between the valence level and the next possible energy level. To put another electron in there once we're already achieved a full valence shell, any electron affinity you would gain, any energy from electron affinity you would gain, would be spent trying to put that electron in. So it's actually going to cost more than the benefit you would get for that. And so it's not worth it. But for this reason, the 2s and 6p form 8. They call this the octet rule. The idea that we want to form a full 8 electron valence shell. Now there is one notable exception to this, and that is hydrogen. Or technically helium, but we really won't be dealing with helium. Hydrogen only has an s orbital. So hydrogen will only want 2 electrons. It's a duet, but everything else will be an octet. So hydrogen only has the s orbital to fill, so it's only going to want to fill with 2 electrons. So how does a covalent bond actually form? The image in the upper right corner actually starts to show this, that if you imagine 2 hydrogen atoms, 2 naked hydrogen atoms that have the proton in the nucleus and the blue electron cloud around it. Well, as these atoms approach each other, the nucleus has a positive effect that's going to start attracting the nucleus between attracting the electron cloud from the previous hydrogen, and vice versa. They're going to start pulling the electron clouds towards each other's nucleus as they get closer and closer together. Eventually, you'll get a point where the 2 electron clouds overlap. And this is our covalent bond. So if these electron clouds are the probabilistic location of the electrons, we have some probability, in fact, now high probability of the electron being found somewhere in this this region between the 2 nuclei. There's a chance that the electrons can be found right here between the 2 nucleuses, and it's higher than the electron being found here. So electron 1, electron 2. This electron 1 still belongs to this hydrogen, but it's found here some of the times, and it's found in this region most of the time. And this electron's found here some of the times and found in here most of the time. But electron 2 is not going to show up there, and electron 1 is not going to show up there. But it's found between the 2 most of the time. So we get the effect of being on loan to the other hydrogen when it comes to making, to counting electrons. So each electron is essentially double counted for each atom. But this is essentially the picture of a covalent bond. What is happening? These nuclei are distorting the electron cloud so that they overlap to form this region of high probability of the 2 electrons. So the first thing we need to do is be able to draw a Lewis structure, a Lewis dot structure specifically. To represent these covalent compounds, we will use what's called the Lewis structure. Now, it shows the compounds with all valence electrons. So we're typically going to be dealing with only atoms in the S and the P region. We will not worry about transition metals, which is why I don't go too hard into the d orbitals or the lanthanides and actinides with the f orbitals, because because we're going to, when we do the octet rule, we're chiefly going to be dealing with these S and P atoms. So we're only going to look at the valence electrons in the atom. So you need to be able to first recognize what group they're in and how many valence electrons they have. We're going to have to show all the electrons either as what we call a non-bonded lone pair or in a covalent bond. So a lone pair means 2 electrons paired together all by themselves. They're not interacting with any other electrons there. The covalent bond is typically a line expressing 2 electrons shared between 2 atoms, an equal sharing. The Lewis structures can contain either single, double, or triple bonds. Single sharing 2 electrons, double sharing 4, triple sharing 6. Technically, we could do 4 quadruple bond, but that's only with transition metals. So once again, we will not see that. But the important thing in the Lewis structure is all S and P electrons are accounted for. So hydrochloric acid H has 1 electron. Chlorine has 7 because it's in group 7. We see 1 from H and 1 from chlorine shared in a single bond. Chlorine has 2. Sorry, hydrogen has 2. Chlorine has 8. It's of its 7 electrons, you have 1, 2, 3, 4, 5, 6, 7. But because of this single bond, it can count on 8 electrons, 3 lone pairs, and 1 single bond. Oxygen, the element, the diatomic element, should have 6 electrons. 1, 2, 3, 4, 5, 6. Because of this double bond sharing, it can count 8. 1, 2, 3, 4, 5, 6, 7, 8. Each oxygen counts 8 electrons, so it's stable. Nitrogen, the diatomic element, has a triple bond because it has 5 electrons to share that it has, and it needs 8. 1, 2, 3, 4, 5, and by sharing it gets 6, 7, 8. Each nitrogen has 8. Each nitrogen is happy. I say happy, it's not literally happy, I'm being hyperbolic, but the idea is that the nitrogen is stable energy when it has its 8. Now, due to this octet rule, there's some strong inverse correlation between the number of valence electrons and the number of bonds any atom will make. Oxygen with 6 valence electrons only needs 2 electrons. Oxygen will rarely make more than 2 bonds. Nitrogen with 5 valence electrons will rarely make more than 3 bonds. Carbon, 4 valence electrons needs 4 bonds. Fluorine with 7 valence electrons only needs 1 bond. And that's true for most of these guys. And in fact, some Lewis structures rely on that fact. Like, for example, phosphorus, the element, is actually tetraatomic. It's actually P4. You don't really just find P, you find a tetrahedral phosphorus structure that each phosphorus makes 3 bonds to another phosphorus. So it makes a triangular shape in the elemental form. Sulfur is a crown structure that has 8 atoms, all with 2 bonds each. That sulfur doesn't actually exist as just S, it exists usually as S8. But it's to get its 8 valence electrons and be stable, you have 1, 2, 3, 4, 5, 6, then 7, 8. So it has 6 valence electrons and shares 2 bonds to make 8. Now, the reason why it's not just like oxygen is because it's actually easier to make a bunch of single bonds. But unfortunately, why is it S8 and not S6 and not 5? It's because the size of this molecule, it's easier to make single bonds and keep the correct, I guess you call it, like, bond angle, the correct shape. So there's not much ring strain when we make this crown structure. But so sulfur and phosphorus and all of our diatomics all rely on this octet rule on why they make these shapes they do. I mean, carbon exists as graphite and diamond in the most common forms, and it relies on the fact that it makes 4 bonds with other carbon molecules. Even Buckminster fullerene, which is C60, which looks like a giant soccer ball, relies on this 4 bond structure between other carbon atoms. But so we're going to go through these steps many, many, many times. But I'm going to try to follow this systematically each time. Though you don't have to follow this systematically, but this is a way to try to avoid some of the trips up when making a Lewis structure. If you know how to make Lewis structures, great. If you don't, if this is the first time you've seen this, Follow these rules. On a take-home test, hey, you can have these rules in front of you. On a normal test, you may have to drill them in. But for the most part, these rules will help you. We will modify them as we get more and more complex. But for now, start with here. So step 1 will be we add up all the valence electrons we expect so we know how many electrons we're dealing with. Step 2, we determine the central atom and put the other elements around it. Now, the central atom is typically the first that would appear in a formula, except for H. And it's the guy that can make the most number of bonds. We would simply say this guy's the least electronegative, the most electropositive, but we don't know what those terms mean yet. Typically, it's the element that's furthest left on the periodic table outside of hydrogen. Hydrogen can only make one bond, so if you have to make more than one bond in a structure, hydrogen's a bad bet. But if you have a chemical structure like CO2 or NO2 or N2O, it's going to be the element that comes first. The element that comes first is going to be the central atom. And usually that atom can make the most number of bonds. Next, we're going to place 2 electrons, placing 2 electrons as a single bond between the central atom and all of its satellites. So every other atom, we're going to try from the get-go to connect them to the central atom with single bonds. So using up all of our valence electrons to make single bonds. Sometimes we may find out there is another way to connect them, but for now, we'll try to connect all things to the central atom. Now, if there's any electrons left, and there usually will be, we're going to add electrons as lone pairs to make an octet or duet on this, an octet on the outer atoms. So add lone pairs to the outer atoms to give them an octet. Now, here's the big thing. If there is any remaining electrons, if there's any electrons left to use, we place them on the central atom. If there aren't any electrons to do, we have to go to step 6. But if there is any electrons left, we must place them on the central atom once we've made octets on all the outer atoms. 6. In order to give the octet rule, we're going to shift the lone pairs from the outer atoms into a double or triple bond to try to give the central atom an octet. Give the central atom an octet. And finally, we're going to verify that all electrons are accounted for and the octet duet rule is obeyed. So we need to double check that all of our structures look valid. So I'm going to work these through. I'm going to write them down up at top. CO2, NH3, HCN, and BH3. So let's go to the document cam. Okay, so let's start with CO2. So CO2, carbon is group 4, oxygen is group 6, and there's another oxygen at group 6. So that means 12, 16 electrons. I've summed up my electrons. I'm going to put carbon in the central position with oxygens around it. And I'm going to make single bonds. Start with there. So that used up 4 electrons. I am down to 12. Next, I'm going to count and say, so this is 1, 2. This oxygen needs 6. So I'm going to use 6 out of my 12 to have this guy have an octet. And I'm going to use another 6 of my 12 to give this oxygen an octet. I have 0 electrons left to place. I can place no more electrons. However, this carbon has how many? 1, 2, 3, 4. How many electrons does it need to get an octet? It needs 4. Now, there's 2 ways you can do this. One of these is better than the other, but one of the beauties of this class is you can justify, if I say valid Lewis structure and not best Lewis structure, there is more than one right answer. So I can take one of these down and move it into a double bond. What happens when I do that? It becomes a structure that looks like this. This guy still has an octet. This guy still has an octet. This guy now has 6. Now I can either take a pair from over here or a pair from over here to give it that last set. So if I go this way, I have this structure. This is a valid Lewis structure. 8, 8, 8. The actual more stable Lewis structure, and we'll learn why that is later, is the symmetrical one, where we have double bond to both oxygens. However, that is our starting point. So both of those are valid Lewis structures. Everybody has an octet. 2, 4, 6, 8 for the carbon. 2, 4, 6, 7, 8 for that oxygen. 2, 4, 6, 8 for that oxygen. Ammonia. NH3. Nitrogen is 5. Each hydrogen is 1. So we have 8 electrons total. Nitrogen appears first, so we put nitrogen in the center. The hydrogens all around. We're going to make 1 single bond, 2 single bonds, 3 single bonds. That uses up 6 electrons. We have 2 electrons left. Each hydrogen only wants 2 electrons. 1, 2. That guy's good. That guy's good. That guy's good. So these last 2 electrons must be placed as a lone pair. Now, this nitrogen is 1, 2, 3, 4, 5, 6, 7, 8. Octet, duet, 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 or doublet, whatever you want to call it. That guy is done. Fully satisfied. Next guy's HCN. HCN. C is 4. H is 1. N is 5. We have a total of 10 electrons. C comes first in the formula, but not before H. But ignore H. So C is going to be the central atom. Make 2 bonds. That uses 4 electrons. We're down to 6. This guy is happy with 2, so we put no more electrons there. This guy is not happy with 2. It needs 6 electrons. 1, 2, 3, 4, 5, 6. All electrons are used. Now, with an octet, this guy only has 4. So what do we got to do? We have to move 1 pair down and another pair down to give it an octet. So redrawing this guy, HC triple bond N. Now you don't have to redraw it each time. You could erase, but I'm drawing in pen. I could cross out, but for clarity, I'm redrawing. 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That is a valid Lewis structure because everything has an octet. BH3. Okay, this guy's the one exception that we will look at. Right. Boron is group 3. Each hydrogen has 1. So a total of 6 electrons. B comes first. H, 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 single bond, single bond, single bond. That uses up all 6 electrons. What do we notice about B? 2, 4, 6. It doesn't have an octet. And no matter what we do, we cannot give that guy an octet. BH3 stands as an exception to the octet rule simply because it doesn't have enough electrons. Boron is often a stickler for that. It often does not have enough electrons to get by. And we'll see that oftentimes boron is one of those exceptions. Now, okay, so those are just quick examples of doing this in process. I'd like to give it an octet, but it can't. There's nothing we can do. There's not enough electrons to go around. But the important thing here is that the outer atoms are satisfied. Sometimes the inner atom, it gets screwed, but the outer atoms should always have an octet or duet. Now, we could do organic compounds. Organic compounds contain mainly carbon and hydrogen atoms, and they're held together through long chains. In these chains, there's typically more than one central atom, because you could have, depending on how many carbons you can have more than one central carbon point, or at least a relative central point where this carbon has 3 hydrogens in another bond, and this carbon has 3 hydrogens in another bond, and this carbon has 2 hydrogens in 2 bonds. So you can have more than one central point and more than one connectivity. Now, when we try to determine connectivity, use the formula as a hint. We'll break down the compound into segments of carbon. Carbon will always contain 4 bonds, with at least 1 bond between one segment and the next. Whatever you do when you do this, do not give hydrogen 2 bonds. Hydrogen can never have 2 bonds. The carbon will always be the one bonded to something else. We do the same with oxygen only having 2 bonds and nitrogen only having 3 bonds. Remember, hydrogen can only make 1 bond. So I'm going to give these examples. So start with the first guy. I'm going to write over here CH3, 3C, and H2. So each carbon will be a break in the fragment. C. Each carbon will be essentially a central atom point. H3, O, C. And then, okay. So starting over here. Starting with the top one. This becomes a little bit harder. So there's 3 CH3s. Each carbon has 4. Each hydrogen has 1. So each fragment here has 4 plus 3 is 7. So 7 times 3, I can do the math for you, is 21 plus 4 plus 5 plus 2, which is 7. So 28 plus 4 is 32. However, we can break this down. Reading this off, That subscript means there's 3 CH3s. So we're going to have a breaking down fabric CH3, another CH3, and another C off the screen. All of those with 3 CH bonds and a single bond somewhere else. Because how many bonds must carbon have? 4. 1, 2, 3, 4. So now, because they're adjacent to this, they're probably bound here. Now, next to a nitrogen, so we're going to put a nitrogen here, NH2. So let's look at this. CH3, 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 all next to a carbon, all next to an NH2. Now let's count over our electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. We've used up 30 of our electrons. We have 2 left. Where do we put them? On the only thing without an octet. 8, 8, 8, 8, 6. Everything has an octet. So the organic, you really kind of have to break it down. This guy is acetic acid, CH3COOH. Once again, carbon plus 3 hydrogens is 7, plus a carbon, which is 4, plus an oxygen, which is 6, plus an OH, which is 7, 14, 20, 24. Now this O in parentheses is going to stand for the fact that this O is not bound to that O. So we're saying this O is going off upwards somewhere. So let's break this down. CH3. Don't do this. Don't do this structure, which I'm going to show you in a second. I've seen this too many times, and I'm just like, our previous organic professor would probably be cringing right now if she could see this. You cannot bridge it with a hydrogen. The hydrogen does not want to have 2 bonds. Hydrogens want to have 1 bond. So CH3. There's a CH3. There's CO. Okay. So how many electrons have we used? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We've used 14. There's 10 electrons left. We will put these on the oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, this carbon does not have an octet. 2, 4, 6. So what are we going to do? We can pull 2 electrons down to make this into a double bond. So I'm going to put a double bond. Now, this carbon has an octet. You could hypothetically pull 2 electrons over, but that's going to be less stable. We'll see about this later. Okay, looking at another structure, CH3, OCl, CH3, O, CH2, Cl. What's in? 4 plus 3 is 7, plus O, which is 6, plus 4 plus 2, which is 6, plus Cl, which is 7. 14, this guy's going to have 26. Breaking it down, CH3, with one bond to something else. O with another bond to something else. CH2 with another bond to Cl. How many electrons have we used? 2, 4, 6, 8, 10, 12, 14, 16. So we have 10 electrons left. Start with the chlorine, which is on the outermost. 2, 4, 6. 2, 4, 6. That gives that an octet. We have 4 electrons left. Put on the oxygen, which also doesn't have octet. 2, 4. That has an octet now. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That oxygen's good. 2, 4, 6, 8. That carbon's good. 2, 4, 6, 8. That chlorine is good. Everything has an octet. Organic should actually be easier than the other ones because there's less exceptions. Everything pretty much has a standard octet. The last one I'll do is HSCN. This is not super organic, but it's organic enough. It's kind of a more inorganic. 1 from hydrogen, 6 from sulfur, 4 from carbon, 5 from nitrogen. 9, 10, 16. So H, S, C, N. Okay, that knocks out 2, 4, 6. So we have 10 electrons left. Start with nitrogen. 2, 4, 6. 4 electrons left. Let's put on the sulfur next. 2, 4. So that has an octet. So we have to satisfy this carbon. How do we satisfy that carbon? Carbon needs 4 electrons. So there is more than one way to do this. I could pull both of these down into a triple bond. I could pull one of these and one of those into a double and a double. Or I could pull both of those into a triple bond. All those are valid options. I could have this structure. That's valid. I could have this structure. And I could have this structure. All of these are valid options because all of these have octets on all 3 atoms. So that's what I'm saying. There is oftentimes more than one right way to do this as long as you follow the octet rule. The organic one will not be super easy. It's something you have to work at. But it will help you to start thinking about this now, especially if you have to take any upper level chemistry courses. If you have to take organic at all, if you're in like some pre-med, nursing, you're probably good. But if you have to take any sort of pre-med, you want to be able to at least have seen this before. So maybe do some more practice problems later. But for now, that's where we're going to start. One of the things we will get to is polyatomics. So when a structure is charged, polyatomic ions, we must add or subtract valence electrons to or from the total electron count. So note, if it is missing an electron, it becomes charged. If it has less electrons than it has protons, it is a cation. If it has more electrons than it has protons, it is an anion. So when we show a charge, we must add an electron or remove an electron from the total electron count to account for this. So when completing a charge structure, if you're drawing this, we should put a subscript in brackets and put the charge as a superscript. Put the structure in brackets and put charge as superscript. So you don't actually have to state where the charge is actually at on the structure. We're just going to put in brackets and put it raised as a superscript. So ClO minus would have 7 from chlorine, 6 from oxygen, and 1 extra because it's charged. So a total of 14 electrons. So when we're looking at this, 2, 4, 6, 8, 10, 12, 14. This oxygen has an octet. This chlorine has an octet. And so we don't necessarily say, where did that negative electron, where did that extra electron go to? We don't have to say it's on this chlorine or that oxygen. We just put in brackets and say the whole thing is -1. Now, the program that I drew this on, unfortunately, would not allow me to leave that thing neutral, so it put it on the oxygen. But I'm not asking that of you. So sometimes, as I said, there's more than one bonding arrangement as possible. These will only differ in the placement of the multiple bonds in the lone pairs. So we could rearrange the lone pairs into various different double bonds. The single bonds will stay where they're at. This difference in bond placement is known as resonance. And the two examples shown here are called resonance structures. So ozone, which is O3, could look like this with O double bond O single bond O. Or it could be O single bond O double bond O. And you may say, well, couldn't I just rotate this 180 degrees and get that there? It's like, yes, you could. But the actual structure is not just a simple rotation, not a simple flip. You actually see experimentally that if I label one oxygen with like heavy oxygen, give it extra neutrons, make it an isotope, you can actually see sometimes that oxygen is double bonded, sometimes that heavy oxygen is single bonded. These are two different structures. And what we actually see, and we measure this, is these oxygens are somewhere between a single bond and a double bond. They're not fully single in length, and they're not fully double in length. They're longer than a double, which is short, and shorter than a single, which is long. So they're like a bond and a half almost. This is due to what's called delocalized bond, which is caused by the shifting or oscillating of these electron pairs. Basically, this double bond can swing up into a lone pair, and this lone pair can swing down to form that double bond. And because this happens so rapidly of these rotating between these two structures, you actually get the average of these two. So you get a structure that is essentially somewhere between these two. This results in what we call a resonance hybrid, which is a weighted average of all the resonance structures. Looking back at the Dock hammer, these three structures can resonate between each other. Now, each structure is not equal. So this one may be, let's say that's 20% of the time. And then these structures flip between the other 80%. So maybe this is 40% and this is 40%. So you'll get a structure that is closer to these two, but slightly like this. So, but a structure that's somewhere between that. So this is going to be a little bit shorter than a single, closer to a double, but sometimes even shorter than us, that 1.5 because of that structure. But we're going to get some ratio of all these contributions to the overall structure. These three would be resonance structures because notice, Still one single bond, 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 one single bond. The only difference is a double versus a triple in these locations. We've moved the lone pairs, but we haven't changed the initial single bond. Okay. I'll go ahead and stop here. I don't want to get into electronegativity just yet. We'll go ahead and get into this on Friday. But in the meantime, so I will send out the email about the tests. I'll also send out a thing on Google Meet. Well, not Google Meet, but on Google Classroom. So look for that. Probably have a week, maybe a week and a half, whatever. But turn it in when you get it done. If you can do last year's test that went over on Monday, you should be able to do this year's test. Should not be that bad. So thank you for your time, and I will see you on Friday for another Google meeting.